Without further ado, tree-based methods, that's chapter 8. We're starting that today, and we will not finish that today. So, so the first section is the basics of decision trees, and I think it's a really good section for getting like the fundamental ideas of decision trees, even if in practice people don't use these kinds of decision trees. So starting in 8.2, they talk about bagging, boosting, barding, and everything. And that seems to be where the action is. Random forests. Can't believe I left out random forests. So I guess that might be next week or in the lab. But this week will be like the fundamental ideas. All right, so we're going to use this situation. By the way, maybe I can make this bigger if I can't make it full screen. Let me see about that real quick. Is that bigger for people or no? Did I do anything?
Yes, it zoomed in.
Much larger.
Okay, good. Okay, so this is the situation they lay out in the book. So I just made this graph. It's a little bit nicer, I think, than when they have in the book, without being that nice. So there are 3 variables here from a hitters data set in the ISLR2 package. The variables that you see in the title are salary, hits, and years. So hits is along the y-axis, years along the x-axis, and salary is encoded in color by the color of the dots. And there's like the median would be a white dot. Red dots are below the median salary, and blue purplish dots are above the median, and it's been log transformed. So American baseball players do not make 6 unit lists, 6 non-united currencies. I don't know. In any case, 6 Bitcoin a year, I guess maybe it would be. Now I apologize. So the idea, I apologize for what's about to come. When we do a decision tree, we're going to basically do this, and I have to make it a little bit smaller, I think. Okay, so now I'm using their graph. So this is the same data, as you can probably tell. It is a bit nice. They made it a square. I didn't have time to fiddle with that. But so when we create a decision tree, when we want to specifically a regression tree, right? Because the outcome salary is a numeric variable. What we want to do is, just like in linear regression, use our features to predict the outcome. But instead of, as in linear regression, having a continuous relationship with a parameter between hits and salary and years and salary, what we do is we divide up the feature space. So here we have a plane, we have a 2-dimensional feature space. And what you can do is create these regions. That's what these R's stand for. So you have a region 1, region 2, and region 3. And here, what you don't see is, or what's not really apparent from this, is that each region will have a corresponding prediction. So for example, for region 1, well, we'll go back to this slide. So notice I'm going to toggle back and forth between these two. So if we go to the raw data without the regression, notice that over here to the left, basically all the dots are red, which means they have a low salary. So the very first thing a decision tree will do is draw this vertical line going up from 4.5, and sort of partition those guys and say, all right, these guys are not making much. And then you can imagine a prior time before there's region 2 and region 3, all of this, everything to the right of 4.5. So every observation for which years was greater than or equal to 4.5 would have been in region 2. And so that would be a two prediction model. But then the model can do one better. It can divide the remaining space in half. And by half, I just mean to create two parts. I don't mean that it's necessarily at the midpoint of any particular variable. But what it does is then among the people for years greater than 4.5, it will divide that again at a certain point in hits. So specifically 117.5 hits to create two more regions. And you can see that if you look at the data, that does correspond to sort of darker blue dots, and then there are also some red dots down here. So that's what the model's doing. And now everyone probably knows this, but why are they called trees? Well, they're called trees because of this, because of how they look. So we can also represent that model as a tree. And in fact, this is a canonical representation, because notice that you wouldn't be able to produce similar graphs for regression trees dividing up space if it were, 3, 4, 5, or 6 dimensions variables. So we have to make recourse to these trees, and this tree encodes the exact same information. But it's good to get some terminology into the presentation. So notice that at the top, we have years less than 4.5. So that is the node. In fact, that's a root node, and the root node is one of a set of internal nodes. So there are two types of nodes fundamentally: internal nodes and terminal nodes, which, because it's a tree, terminal nodes can also be called leaves. I believe that's what I'm gonna get around to saying on the next slide. Yeah, so we have terminal nodes or leaves, internal nodes, and again, because it's a tree, all of the lines are branches. Some of the things that we note, at each internal node, there is a splitting rule. So basically, how is the data going to be partitioned? So the very first one is years less than 4.5. And by convention, if this evaluates to true, you go to the left. If it evaluates to false, you go to the right. And another thing to notice is that whereas in a linear regression, you would have an infinite number of possible y-hats. Actually, perhaps that's not true, because years and hits are both discrete variables, but you have a lot of y-hats. Here you have 3. There are exactly 3 predictions that this model can make. So you see those down here in the leaf nodes. All right, so that's the basic stuff. Oh yeah, and you kind of get this heuristic encoding of variable importance. So one way that you can interpret years being on top at the root node is that it is the most important variable, and that'll get fleshed out a little bit later, but basically most important in reducing variance in the salary variable. Okay, so here's a quiz for everybody, just to be fun. So, and this is, it's a better quiz if you haven't paid much attention to the book, I guess. But why is this here? By this, I'm trying to circle indicate this partitioning of space on the upper left. What is that about? And I'm gonna sip some coffee while people meditate on that. And for people who know why it's there, they can just sit smugly.
So you only want people to answer who don't know the answer.
No, that's not true. It is funny that you say that. I want people to answer who were not spoon-fed the answer, as I was. So this is not a criticism of people who.
Justin, I'll jump in.
All right.
Those are your groups, correct? It's the allocation of likeness to each one of those, so that's your main branches between the. It's the not the terminal node. What's the internal node? That's where you're branching off to create these groups, correct?
That is a correct definition of internal node.
Okay.
Now, there's some, and then just in the interest of time, I'll say what's going on. The upper left-hand quadrant is an impossible partitioning of feature space.
Okay.
It is one that no regression tree will get you to. So, and you can think about why. So remember that at a root node, the data set is going to be split in half. Again, that doesn't mean that half the data set goes one way, half the other way, but just that there's a split such that some proportion goes one way, some proportion goes the other way on an independent variable. Notice here that, so what we could do is we could look at this plane and we would say, all right, did it happen on X1 or happen on X2? And the characteristic thing you would look for is a line that goes from basically, I mean, if it were on X1, it would go from, I guess we can imagine that being the X-axis all the way to the top of the graph. And if the initial split were done on X2, it would go all the way from, I'm going to call the Y-axis all the way to the end of the right-hand end of the graph. And notice that that's not there. And so this just is an impossible way of making a split. And I guess accordingly, they don't bother putting the different regions, right? They don't do R1 or 2 or 3, etc. So anyway, so that's just a useful thing to know, is that some splits, some partitioning of the data spaces can't happen, even if they're lines. So you might think, all right, sure, decision tree, they have to have these kind of like either vertical or horizontal splits, but they also have to have like very thoroughgoing splits. Anyway, so you can see that in now moving over to the second, well, I guess this is actually the first quadrant if we were doing a Cartesian plane. So anyway, so we went from the second quadrant to the first quadrant. And so notice exactly here, they very helpfully, and I'll zoom in a little bit. Oh yeah, that's how I zoom in. So they've indicated T, again, we're back in tau land, so I guess that's what our cut points are going to be called. So T1, so the first cut along X1, and then I'm not going to go through this because everyone can see this, but there's 2, 3, and 4. And there's something particularly interesting about this particular partitioning of space, but you do see they have this nice graph down here. And so now when we have a 3-dimensional, basically now we can encode Y, and they've done it in this 3D way, but you could also do it with like a heat map or something. But that's basically what it looks like. So these sort of planes, these plateaus are values of Y. And here, notice 1, 2, 3, 4, 5 different predicted values. So we have 2 more than previously. And that again corresponds in a one-to-one way with the tree representation. There are 5 regions, 5 predicted values, 4 cuts. So anyway, some vocabulary. Let me zoom out. Too far. No. Aha. I got you. Stratifies, so you'd say a tree stratifies or segments observations into regions. So there you go. All right. So now it's time to now I have this kind of impressionistic understanding. It's time to get into the nitty-gritty. So it's a regression tree, right? So it's a regression problem. So we have a quantitative outcome. So we can get residuals, right? Which are we can square our residuals to get a loss function, and we can get residual sum of squares. And here's what that formula looks like. And there are a lot of double summations here, and I discovered that a very nice way to start understanding all of them is to just not pay attention to the leftmost summation, figure out what's going on in the inner summation, and then kind of expand it out. And so all this is a sum of squares where, again, ignoring the leftmost summation, you're taking your observations, and you're basically getting the variance. Notice that that's what that is, right? So it's your individual observations minus in this case, it's the empirical mean for a region J, right? That's what the R under subscript J is. And then basically the left-hand summation just says for all the regions. Okay, so that's what this is, and that's what we want to minimize. Again, OLS, you want to minimize residual sum of squares. With the tree, you want to minimize residual sum of squares. It just has this particular form. Now, the tricky thing is finding all the possible regions is computationally infeasible. It's not possible. So what do we do instead? And this is again from the book. That's why it's quotation. That's why there are quotation marks. So we take a top-down greedy approach that is known as recursive binary splitting. Now, there's a lot of vocabulary in that, so that's why it's in bold. So top-down. So it's basically again, think back to the trees. We start with all the observations belonging to one group, one node at the top, the initial root node. So that's the top-down. Now, greedy. I'm just going to quote from them. So it's greedy because at each step of the tree building process, the best split is made at that particular step, rather than looking ahead and picking a split that will lead to a better tree in some future step. Now, I don't know if it's just me, but when I looked at that definition of greedy, that explanation of why greedy is there, I thought to myself, it seems like a better word would have been myopic. Because the main characteristic there is that you make the best split at a particular step rather than looking ahead and picking this blah, 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 right? So the whole rather than looking ahead part seems to be more myopic, but greedy is actually a technical name for a type of algorithm, for, again, this type of algorithm. So it's just the way it is. This is not an idiosyncratic choice of the authors. This is what these types of algorithms are called.
Do you know, I don't think the book mentioned, but do you know if there are variations in less greedy tree algorithms?
The less greedy trees. Let me think. Yes, there are. So there, okay. Okay, in a way, no, but yes. So there are ways of getting non-greedy results by combining a lot of trees. So next week, when we talk about random forests and BART, those are ways of getting around the problems that greediness, I mean, greediness is a vice, as everyone knows. So it causes problems, and there are ways of getting around it. That's what I'll say. But so I guess it's like a stay tuned, is my answer to that. But I did want to say, so again, so recursive binary splitting, so it's just, I'm going to put that on hold for a second. So this is from this website, brilliant.org. I don't know if you all have heard of it, but they have like basically wikis for different things. So they have actually a wiki for greedy algorithms. And I mentioned that, greedy algorithms can cause some problems. And basically the problem is finding local minima or local maxima as opposed to the global ones. So here they have a really nice, very clear example of this. So here's an algorithm that has that. So here this is different, right? This graph, again, the set of nodes and edges is established, whereas a regression tree is going to create them. But the goal of the algorithm, as it were, is to find the path along the graph that results in the largest summation of numbers, right? So what it does is it starts at 7 because it has to. It looks at 3 and 12 and looks at which one is bigger, and chooses 12. And then here it looks at 5 and 6 and chooses 6 because 6 is bigger, right? So at every step, it's finding the largest number because, again, it wants to sum to the largest number. So that's what it does. Now, you'll notice that if it had foresight, if this greedy algorithm were not myopic, what it would do is forego the 12, take a hit of 9, go to 3, and then go to 99. But it didn't have access to that information. So this is a nice example of a greedy algorithm not choosing the best path in a different application. But the same thing could happen in trees, because it's you know, path dependent exploration of feature space is a fancy way of saying what can go wrong. All right, any questions about that? Now I'll get on to the binary splitting part, if there are no questions. Great. Okay, so this is a lot, but it's fun. So what happens at these splits? To me, it's kind of a small miracle. Apparently, this can be, I mean, it is implemented very fast, but when you think about what's actually going on, it's pretty wild. So you have p predictors in your model, right? So this is, again, it's a regression problem, so you know, we can represent it in the same way, our independent set of independent variables in the same way. So x1 through xp. And so at each split, the model considers all predictors and all possible values of the cut point again. So this is, you know, again, assuming that our independent variables are continuous, right? You can put a cut point anywhere in it. And so you choose every combination of predictor and cut point such that, well, with the goal of minimizing the RSS with one split. So I don't know if it's worth it to get into the actual, you know, the stuff down here, but this is what this is what it would look like if we wanted to like sit here for a while. But basically, it's a minimization problem. I'm going down to the last line. So you know, you choose J, which is choosing your variable. That's the index for the different predictor variables. S is the index for the cut point, and you choose J and S such that you minimize the residual sum of squares in both branches. That's why there's a plus there in the middle. So this is actually, this is a useful equation to come back to. Maybe we'll come back to later. But anyway, that's what you're doing at each. So like this is feasible, and that's what I was trying to indicate earlier, is that to me it's kind of wild that this is feasible, but this is the problem that's solved bit by bit instead of doing this intractable problem, which I now have up here. So this is, can't solve this, you know, this residual, you can't minimize that just like that, but you can approximate that, or you can try to get to that by doing this stepwise solution. And then, so this is, you know, so it's recursive binary split was the piece of vocabulary that we're kind of talking about now. And it's recursive just because you can keep going back to the p predictors, all p predictors, and keep splitting them. Okay, so here's a bushier tree. Again, bushier is, I don't know if that one, so we have, you know, for tree vocabulary, right, we have a root, we have branches, we have leaves, now we have bushiness. So we're accumulating tree vocabulary. All right. So here, notice what happens. So this is the original split, years greater than or less than 4.5. And previously, that just went to a leaf node or leaf. But now here we see that there's RBIs down here, put outs, years, right? So it is much bushier. There are many more terminal nodes. And there are now 5 where there was once 1. And here down on the right-hand side of the split, there are now a lot. So this brings up another question in the algorithm, is like, why was the other one kind of stumpy? There, I'll throw in another one. Why was the other tree kind of stumpy, and why is this one so bushy? And that brings up the question of, how do you know when to stop partitioning space? So to find the best model, we'll get to that in a second, but typically these models are fit until each node has under a certain number of observations in it. So you could say, I want to partition space, feature space, until each node has fewer than 5. That would be like a typical way to stop partitioning space. And they don't have any indications in the book of like how to set that, like what would be a good justification. But you can imagine that once you get fewer than like 5 observations in a given node, that you're really just fitting your model to noise at that point.
Now, wouldn't it also
So-
be though, like if you have, let's say you have 10 observations in a given node, but they're all the same outcome variable, you wouldn't need to split it any further, would you?
No, I don't know how you would. That's a good point. I don't know how this is implemented under the hood. I was thinking about that a bit though, like because I hadn't thought of it before reading this chapter, even though I had like not a good knowledge of trees, but I'd like seen them used before and stuff. And so yeah, this idea of having it be every node under a certain number of observations, that was like, okay, that makes sense. But yeah, I hadn't thought about this when that becomes impossible. That's a really good point. They do mention and they're arriving at that criterion, the like stopping rule, that one might think a good stopping rule would be to stop partitioning when, or to just simply not make a partition at a certain point when you don't get a desired decrease in residual sum of squares for the overall model. They say like at first blush, that's a good way to do it. But they point out that that stopping rule is too myopic. So you can maybe not have a good split somewhere. So it reduces residual sum of squares by not very much, but then the following one will reduce residual sum of squares by a lot. So that's why that particular one isn't used. Yeah, so I thought that was interesting. All right, so okay, so here we figured out how to grow a big bushy regression tree, but now how would we choose? This is the next question. How would we choose exactly how bushy to leave it at the end? So this is something that I found interesting, is that basically we are going to fit this big tree and then work backwards from there. Okay, so how do we work backwards? By cost complexity pruning, also called weakest link pruning. So basically, we have this big tree T naught, and then you have like the magnitude bars over here to just denote the size of the set, but that's going to denote how many terminal nodes there are, and we prune it back to a subtree. And I should have put, for good practice, I should have put a T after subtree, because that's what this T will be here. So basically, what happens here is the exact same thing that happens with lasso and ridge. You have the loss function again here. It's just the sum of squares of the residuals, and you're adding to it a penalty, so which is just alpha times the number of terminal nodes of leaves. So you can think of it as, and again, like because it's a binary split every time, you can really think about this magnitude as, you can also think about it as the number of nodes. Like there's just a difference of 1 between the difference of splits in terminal nodes. So the way I think it's the most intuitive to think about this is that, if you want to make a split, alpha is there, this whole, I guess the whole factor there, but weighted by alpha, is like saying, all right, you want to split, that'll cost you whatever alpha is. That's the way that I like to think of it. Very much similar again to the lasso and ridge regression, where if you want to have some beta kind of not be 0, some parameter in the model not be 0 or move further away from being 0, you have, in that case, lambda is typically used to say like, all right, that's going to cost you. And it might be worth it in terms of reducing residual sum of squares, it might not. So anyway, that's what's used here to penalize complexity. And so with that equation in mind, we can now go to the algorithm here for finding a final model. So basically, what I said earlier, you go a large, bushy, nodey tree on the training data, stopping when each terminal node has fewer than some minimum number of observations, I guess barring the possibility that you have a completely homogeneous node. All right, so then we do this thing. We apply cost complexity pruning. So the equation on the former slide to the tree, the big bushy tree, going in step 1. And what that will do is it will obtain a sequence of best subtrees as a function of A. Now here's an interesting thing about this algorithm is that now you set that aside. So you have your training data, you have all your training data, you grow the big tree, and then you find a sequence of subtrees that corresponds to different levels of alpha. But then you set it to, you set it to the side, and you have k-fold cross-validation. And so what you do, so we'll just say it's 5-fold, right? So you have 80% of your training data. And so you basically do steps 1 and 2 on the 5 different possible or the partitions of 80% of your training data. And for each one, you have the left out 20%. And so you see how good your out of sample predictions are on the, let me see if I have this. You see how good your out of sample predictions are on for different levels of alpha. And here mean squared prediction error is what they write, but you don't have to use mean squared prediction error. But anyway, but some estimate of a model goodness. And that is how you determine which level of alpha you ultimately use. And so then once you've got these estimates of model performance at different levels of alpha, you kind of throw that information to this, well, not all the information, but you have your one value of alpha, and you go back, you bring back the tree that you grew in step 2, and whichever tree corresponds to that alpha is the one that you take. So I thought that was an interesting.
I have a question that I'm still kind of thinking about how to word this here. So this process you've described is a way of finding a value for alpha. It's like tuning alpha.
Yes.
But you tune it on, let's say, data sets that are 80% of the size of your full data set.
Yeah.
But then you might use that value of alpha on 100, your full data set. It seems to me, just thinking through it now, my intuition is a little fuzzy here, that if you can go back to the slide where the alpha, alpha is in the thing you're minimizing. Yeah, there. It seems plausible to me that alpha might scale with like the density of your data set, right? Like if I have, just for imagine like a scattering of data points, like you've shown before, and I just take out half of them, then for a given partition, the contribution of that first term to the RSS, the y minus y hat squared, like that will have a bigger value per partition because there's more data points in each partition. And so sort of the alpha needs to kind of balance that. I don't know. Do you see where I'm going with this? Like the value of alpha seems like it should scale with the size of your data set. Like the cost for making a branch, I'm willing to pay a higher cost than just more data points in each thing that I'm partitioning.
Right. That's actually, I had not thought of that. That's a really interesting point. And let me see. So hold on to that thought for a second. And okay, actually you can already apply it. So how does that intuition or that thought play out here? So notice what goes on in this is kind of okay. So what we have here is, and I guess I just want to know if that intuition plays out at all in this graph, in this plot. So here the 3 lines are the mean squared errors, but we have training, which you can kind of ignore. I think you have the cross validation, right? So this would be fit. So they did 6-fold CV, right? So you have 5/6 of the data used to fit the models that correspond to the sort of teal dots. And then you have the test, which interestingly is, well, perhaps not interestingly, is always lower. So like that was a thought that I had. I mean, here it's very systematically lower, and I don't think that's an. I mean, this is a thought I had that was not as I didn't go as near as far as what you were saying, but I did think about how, like what does this mean that the test error is always, and I would say like systematically. I mean, you can even get to the end and say statistically significantly lower than the cross-validation error. And I feel like that has something to do with what you were saying, but maybe not.
I think, I mean, that seems consistent with it. I mean, here they're the x-axis here is tree size, so that's sort of, you know, like standardizing some measure of the complexity. But yeah, I think maybe because, well, how big is the test set in this case? I guess it might be relevant. Like, is it the same kind of partitioning?
Well,
just half the data set.
I don't know if they did half and half. I honestly don't know. I guess what I was thinking of is, regardless of the size of the test set, you know, here, like, so like the teal dots are fit with, you know, 5/6 of the data, and then right, so it's like, so these had the benefit again of 5/6 of the training set, whereas the orange dots are, you know, evaluating a model that was fit on all of the training data, so it had an extra 1/6 to fit it. So that's this simple. That was my simple thought. But and I don't know how. The tricky thing is, I don't know if that's an idiosyncratic feature of this particular example. Again, I thought not, kind of for reasons about what you were saying, but I don't know. In any case, I don't know. Does anyone have any thoughts relevant to these things? Germane thoughts? No germane thoughts? Germane sounds like a tree word. I'll try to use germane at least one more time in this lecture presentation. Okay. Oh, and I have here, even though I looked at the time and I thought, okay, I need to speed up. And then immediately I just got distracted by my fun tidbit that this is 6-fold CV. Earlier, we had a discussion, weeks ago, we had a discussion about how to choose, like, you know, is it just completely arbitrary to say 10-fold cross-validation, 5-fold cross-validation? Here, they chose 6-fold because the number of observations in the training data was divisible by 6. So there's a new way of choosing how many folds in your cross-fold validation is, what can I divide my training data into without remainder. Oof. All right, things should go quickly now. So really, regression trees gave us the framework for this, and for classification, the biggest change is that, you know, we have a categorical outcome. So, oh, and I just put a note in, theoretically any number of classes. The example in this that they give is a binary classification problem, but it's not like logit where you're, well, okay, there's a binary logit and then there's a multinomial logit, but people typically think of 2 classes. But for a tree, you can have any number of classes theoretically, but I mean, I assume it would just start falling apart at some high number of classes. And really all these slides are going to address is how you would implement this in the classification how you would implement the algorithm for classification problems, because as you can imagine, residual sum of squares is not going to work. I'm just trying to think, should I come back to this? Well, at the end, I guess I'll just preview, you know, I'll spoil this. Here, notice that now leaves, instead of having numbers, they have categories. So, which is what you'd expect, right? You want categorical predictions. So, yeah, but still, they're still predictions. I mean, it's still really the same thing. We have splitting rules, binary splitting rules, and, you know, a series of them. It's recursive, and then we end up with predictions. So yeah, so same deal. Here we see, training cross-validation test. Again, we have a different y-axis. We have a different metric of how good our model is. Here it's just prediction error. And then this would be the cross-validated model. So, but again, that's kind of the spoiler. That's what we end up with. We now need to think about how to get there. So as the slide is helpfully titled, if not residual sum squares, then what? So the first thought one might have, if they bring up in the book, is minimize classification error rate at each split. Again, so this is the decision for, this is the decision rule for what we do at each split. Where this, I'm not going to go into this equation. I just will rely on people's intuition that of what an error rate is. But yes, it does depend on the proportion of training observations in the M3. This is actually going to be a symbol that keeps coming back. But here's what they write. They write that it's not sufficiently sensitive for tree growing. So it's not going to work. And they propose two alternatives. One is the Gini index, which people have probably heard about more in the context of describing income inequality. But here it is in our application. So let me think about how much to go into this equation, because it is okay. So so it's a summation of, now some of you may remember from statistics days of describing the variance of a Bernoulli variable. Yeah. You have, so again, it's like for example, the variance of a coin flip, assuming it's a fair coin, would be 0.5 times 1 minus 0.5, which turns out to be 0.5, right? But if it were an unfair coin, if it turned up heads 80% of the time, it would be 0.8 times 0.2. So so that's how you can think of this. It's easiest to think about in the two-class case, but again, K could be any number. It's just the number of classes that you're trying to classify. But you do this, notice the summation. So it's a total variance across the K classes. So for example, if I had a node, so if I want to get the Gini index for a node that had 80% of one class and 20% of a different class, right? I would say, okay, class 1, so K equals 1. I would do 0.8 times 1 minus 0.8. And then I set that to the side, and it's a summation. So I need to add that to 0.2 times 1 minus 0.2, which is 0.8. So that actually turns out to be the same thing. I mean, 0.8 times 0.2 times 2. Anyway, so that's the Gini index. And it's a measure. In the book, they say it's a measure of node purity, but I think it's really a measure of node impurity. It seems more intuitive because G increases as impurity increases. So anyway, that's just a pedantic note on my end. An alternative to a Gini index is entropy, which I'm not going to go into the equation because I think it's easiest to just look at these. So I made these graphs where this is just what it looks like. So you have a two-class case. And so like as soon as you have a majority, so 0.5 basically is the smallest proportion you can have and be a majority. And then these are just the curves of what happens as the node becomes more and more pure. So you can see basically, proportional majority class, I think, is very clear to people intuitively. And this is what happens as to the entropy in Gini as that happens. So you can see that, they're not the same, but they look incredibly similar. They have, they would do the same thing. They perform the same thing. And so here's what number of classes 2, number of classes 3. And so anyway, I don't know if these are enlightening at all, but that is what the functions look like. So here is an interesting thing. This is it's actually my last slide about classification. So I want to point everyone to this curious thing here. So notice, I just noticed the word old peak, which I think is funny. But let's just focus on this, these two leaf nodes here, where resting ECG is less than 1. So the split is to the left less than 1 here, greater than or equal to 1. Now, you might think, why in the world would a split happen where I'm predicting the same thing on both sides? Like what? So this split, so you can imagine erasing this split. So removing the internal node, and in the model classification error would not change because it's going to predict yes either way. So why does this happen? And then this is actually going to address something that I left really kind of vague earlier, and I felt guilty about it when I said not sufficiently sensitive for tree growing. So I'm going to make good on, I'm going to cleanse my conscience. So here's like why that type of thing would happen. So here's the example they have in the book, and it's actually from that specific resting ECG. So they say the split, and then they're referring to that split, but it importantly doesn't change the predicted class. It's performed because it leads to increased node purity, right? Because we're using the Gini or entropy as a way of determining splits. So what happens is that all 9 of the observations corresponding to the right-hand leaf have a response value of yes, whereas 11 of those corresponding to the left-hand leaf have a response value of yes. So now that's what they say in the book. And if you actually take out pen and paper or calculator, as I did, I said, okay, so all right, so here's what you do. You start with 16 of 20. So this is imagining we erase that internal split and just make it a leaf. Then we'd have 16 of 20. But instead, what actually happens is we have 7, 11, and 9, 9. So how does, for example, I'm just gonna use the Gini as opposed to entropy. Like how does it look before and after? So, come on. So before, what you would do is you would just do this multiplication, you'd have a 0.32. Afterward, you have 0, you have a completely pure node. So it has a Gini of 0, because again, all 9 were the same class. And then you can calculate the Gini for the other one, and you get 0.463, and you say, oh no, it's higher. But then you weight them by how many observations are there, and you see indeed that if you were to have not made the split, you would have a total of 6.4, whereas after making the split, you have 5.09. So that's why you get these, I don't know, leaves, bifurcated leaves. I don't know, I'm trying to stick with the tree, the tree idea. Anyway, so I thought that's interesting. So that's why these types of things happen. That's why these types of things happen. And that is why node purity is used as opposed to, or node impurity is used as opposed to classification error. All right, so this is the conclusion, good. So the thing that they address towards the end of this is, okay, so, you know, ordinary least squares or just linear models and trees, you know, they're both regression models. We're predicting, well, we're going back. That we were doing classification, now we're going to go back to a continuous variable. And they're like, which is better? That's, you know, a relevant question for a modeler. And the answer is there's no answer. The answer is it depends on the actual decision boundaries. Or decision boundaries, the actual, depends on the data and the underlying process. So here, I mean, this is just very intuitive. So reality is held constant across the, I guess, well, across these two models here, right? So it's a linear difference. Wait a second, this is actually classification. Just kidding. So so again, so if the boundary is truly linear, then you'd want to use a logit. And then because this is what recursive partitioning, this is what a tree would do to that decision boundary, right? So it makes sense, you know, you see again, I guess first split was going to be here. So at x is, you know, minus 0.3, sorry, x2 is minus 0.3, and then it kind of goes and does the best it can. But why would you do that when you could do that? But then you might have a case where the decision boundary is more like this on bottom. And so linear model is not going to do great. It obviously, you know, it might do okay in terms of like observed prediction and whatnot. I mean, in this case, it wouldn't do super great, but it might, but it just doesn't correspond to reality, whereas a tree model would. So there's no hard and fast answers, is basically. Yeah, this isn't super important. I mean, it is important, but after, it's just, you know, the notation. So it's just important to note that when you know, run a linear model, you're assuming a certain functional form. And when you run, if we had gotten to the lab, we'd see that, you can either use tree or R-part for recursive partitioning. You assume this functional form. So these are just assumptions you make. And then super fast, by way of concluding bullet points, this is something I didn't talk about, but it handles categorical data, it being the tree, handles categorical data in a really intuitive way. And that extends to handling missing data in a very intuitive way. One thing they don't mention in the book is that it can do variable selection. So if you run a tree model, it won't, again, with P predictors, it won't necessarily use all P predictors. So in that sense, it performs variable selection. They don't mention that in the book, and it makes me kind of question why not. Maybe I'm wrong about that, but it seems like it does. So I just feel like it's an important point, so I'll mention it, even though I'm running out of time. We all hopefully remember that one of the benefits of Ridge and Lasso is that you can actually have a feature space that is bigger than the number of observations. And that's like one of the benefits of these. And that's also one of the benefits of forward stepwise selection. That was that week. And you just can't, and like just using ordinary least squares, you can't fit a model where you have more predictors than observations. And it seems like, I could be wrong again because they don't mention it, but it seems very intuitive that with a tree you could fit a model that has more predictors than observations. Anyway, so I thought that was an interesting point that they didn't mention, but so maybe I'm wrong about it. Actually, these models is an interesting historical note that these models were developed in the social sciences to discover interactions between variables. So something I didn't really cover, but it's there. They mention as well that it's intuitive for decision making. So, there was like I didn't really go into the details of the data, but the classification example was medical data. So you can imagine like a doctor being like, using these models to make decisions. So people think that actually trees might kind of mimic actual human decision making. So that's why it's intuitive, because it matches what humans do. And then the biggest downside is they mentioned that performance can be low, which is actually going to be the subject of next week's. So remedying the not great performance is going to be the subject of next week's presentation. And with that, I conclude.
Awesome. You nailed the time and covered good information. So thank you. Does anyone have any comments or questions or other thoughts, observations? Okay. Then I think we'll discuss in the Slack, and I'll see everyone next week. All right.